today is just continue. Okay. The lesson that we have last time. So we have started already with chapter 16. We started with what we call the buffer. And we end up, okay, with some problems in the buffer. So to refresh you, buffers are just solution that is made up of weak acid and its conjugate salt, or weak base and its conjugate salt. So if you have a weak acid, then that means that's a conjugate base, and the conjugate base would come from your salt. And if you have a weak base, okay, your conjugate acid would also come from your salt. And we know that if we have a buffer, we're just going to use this equation. So I would suggest you memorize this equation because this will be handy to you, not only in your third exam, but also in your final exam. Okay, so before I say goodbye to the buffer, I would just like to solve one more problem about the buffer. Okay, so we end up with one question that was not what we called solved during that time. And that question is, describe how would you prepare a phosphate buffer with pH of about 7.40. So the thing that you're going to ask yourself here, okay, you are going to work in a solution that has a pH around 7.40. So the first thing for you to do is find out what system of buffer has that pH, or at least a pKa on that thing. Because if you're going to look at the Henderson-Hasselbalch equation, we have what? pH equals to pKa plus log of your conjugate base over acid. Okay, so what happened? Or when do we have a situation where pH is equals to pKa? Anyone? When does it happen that the pH is equals to the pKa?
When the concentration of the acid, when the acid and the conjugate acid is equal, because then it'll be just log of 1, which is 0.
So when the concentration of the acid and its conjugate base are equal, this happens. Because what happened there? You will have what? Log of 1, which will be equals to 0. So if we're going to look at the system of the buffer, so we have there table 5, 15.5. So there's one system there wherein you have the phosphate system. Okay, so the phosphate system, it goes to this one. It goes to this one. So in each of them, you have what we call the particular Ka. So if you're going to look at the Ka that they have there, so this is 7.5 times 10 to the negative 13, oh, 3. This is 6.2 times 10 to the negative 8. And this is 4.8 times 10 to the negative 13. So if you're going to get the corresponding pKa, so this is around 2.12, 7.21. So among these, which species do you think meets the pH that we need? Anyone?
H2PO4.
Okay, so as you could see there, the pKa here is the one that meets that need. So this is where you have a reaction of H2PO4 minus dissociating to give you HPO4 2 minus plus H3O plus. Okay, so that means we're going to have a system that contains this as the acid and this as the conjugate base. Now, if we're going to look at this, so you see that the pKa is 7.21. So we're looking at 7.40. We have a pKa that's 7.41. So all we need to do now is determine the ratio of your HPO4 minus over H2PO4 minus. So try to solve. What do you get? So 7.40 minus 7.21. So that will give you what?
0.19.
So what does this mean here?
To get rid of the log, you need to
If you're going to get rid of the log, so that means this is what?
10 to the 0.19 is equal to the concentrations.
So try to calculate.
It comes out to 1.55.
So you got
1.55.
So how do we interpret this value? Anyone? So to
It's
interpret this value, we could say for every
It-
1.55 moles of the HPO42 minus, you have 1 mole of H2PO42 minus. So that's the mole ratio that you have. So all you need to do now is determine it in mass, but you already what we call solve the given problem. Analyze.
Professor, for this reaction or for the the phosphate buffer, it's always going to be 1 mole of the concentration of acid or weak acid.
Yeah, that's how we set this up because of the mole ratio here. So it's always like, if you're going to get that one, that is always over 1.55 over 1. Question? Before we move with titration. Question? So the next thing that we're going to talk about is titration. So I'm not sure if you're familiar with titration, especially if you don't have this what we call in-person class. So whenever we do titration, we're monitoring the pH. Okay, when a titrant is added to an analyte. So what you have here in a titration, so maybe I'm just going to show everything here. So you have here a titrant that is in the burette, which you add to a solution that is in a receiving class called the analyte. So the idea there is you're going to determine the concentration of the analyte here by adding the titrant. So a solution of accurately known concentration is gradually added, so that's the titrant, to another solution of unknown concentration until the chemical reaction between the two solutions is complete. So you're adding this known, you're adding a solution of known concentration to a solution of unknown concentration. And what you have here is, at the end of the so-called equivalence point, you can determine the concentration of the unknown solution or the solution of the unknown concentration. So at equivalence point, so that point, that's the point in which the reaction is complete. At the equivalence point, usually you can get this, the mole ratio that they have. It can be a 1:1 mole ratio, 1:2 mole ratio, 2:1 mole ratio. Okay. What you will know is at the equivalence point, there's a relationship between the titrant and the analyte. Now, how do we go to this equivalence point? Usually we add something known as indicator. This usually changes color at or near the equivalence point. So if you're going to look at this one, so from a colorless sample, it becomes pink. So you have here an indicator known as phenolphthalein that is added to the solution, which is usually an acid and added with base. So at equivalence point, there's a 1:1 mole ratio of the acid or the base. Now there's an alternative method on that. In the lab, if we're doing 112 lab, usually we use a pH meter. And how do we determine where is the equivalence point? Usually, when you keep adding your what we call base, it will just come a time that there's a steep change in the pH upon addition of your base. Okay? So we can have a strong acid, strong base titration, such as this one. So this is NaOH is what? How do you classify NaOH? Anyone?
A strong base.
Okay, so that's a strong base. And then HCl,
Strong acid.
okay? So HCl is a strong acid. So you have here a reaction of a strong acid and strong base. But if you're going to look at net ionic equation here, it's just really the hydroxide and the H plus that is reacting to produce H2O. And if you're going to look at the equivalence point that we have, this is what it says. What can you say about the equivalence point? Look at the pH.
It's neutral.
So the pH is neutral, right? So as you could see there, strong acid, strong base, they will give you a pH of equals to 7 at equivalence point. And look at the changes that you have. pH, let's say, initially it's 1 because you have, let's say here, a 0.1 molar HCl. Okay. And then it is added with the 0.1 molar NaOH. Okay. So as you add base to it, the pH increases. Does that make sense? When you added base, the pH increases. Yes, the pH increases because you're adding what we call base, because base usually has higher pH. Now, what happened when instead of a strong acid, we use a weak acid titrating with strong base? Like for instance, we have acetic acid reacting with NaOH to produce sodium acetate and water. So if we have that, okay, so we have this. So the one that is reacting with acetic acid is really hydroxide. Okay, producing acetate and water. Now, what really react at equivalence point? The one that react at equivalence point is your acetic acid reacting with water to produce hydroxide and acetic acid. Acetate reacting with water to produce hydroxide and acetic acid. And this is the reason why the pH at equivalence point is equals or greater than 7. Try to look at it. So, what's the thing that you need to remember here? If the titration is between a weak acid and a strong base, the pH at equivalence point is more than 7. Now, to answer the question why is it more than 7, this is the reaction that happened. To answer the question why is it what we call more than pH 7, because you have a strong base and the other one is a weak acid. Remember the salt that we have? If the salt comes from a strong base and a weak acid, your salt will become basic. So the same thing here. So the example that we have here is at equivalence point, the pH that you have is 8.72. Now let's try to solve what is the pH when you're doing titration. So this is can be one of the questions that you have in your exam. So for instance, this is the question. Calculate the pH in the titration of 25 ml of 0.1 molar acetic acid by sodium hydroxide after the addition to the acidic solution of the following. 10 ml of 0.1 molar, 25 ml of 0.1 molar, NaOH, and 35 ml of point. But before that, maybe we can do this one. So this is what? Before titration. So what do we need here to solve this problem? We need the pKa or maybe the Ka. So we have here acetic acid. So what is the Ka of acetic acid? (1.8) times 10 to the negative 5. I'm just going to get my calculator. Okay. So how do we solve the pH before titration? So this is just typical weak acid. So you have what? 0.1 molar, 0, 0, and then what? Minus X plus X plus X. And you have here 0.1 minus X, X, and X. So if you're going to do it, it's 1.8 times 10 to the negative 5. You have X times X over 0.1 minus X. And then the assumption that 0.1 minus X is still 0.1. So what do you get?
I got 1.34 times 10 to the negative 3.
Okay, 1.34 times 10 to the negative 3. And the X there that you have is the H plus. So all you need to do is get the negative log of that. And what's the
Ye-
pH that you get?
2.87.
2.87. Analyze.
Did you subtract the 0.10 from the 1.8 times 10 negative 5?
Question?
Where did the 0.10 go?
Huh?
Where did the 0.10 go?
Where it the what?
The 0.10, where did it go?
That's the given one here. You cross multiply this with this one.
Okay, so you multiply it and then you get,
That's the X squared. So to get the X, you get the square root of that.
oh, okay, thank you.
So how do we interpret this? Before the titration begins,
Professor, I have a question.
okay,
For the Ka value, we're going to be giving that into
it
question.
will be given unless that's the one that's being asked. So that means at the beginning of the titration, before you add anything, the pH of your solution is 2.87. So when you add the 10 ml of 0.1 molar NaOH, so that means what happened to the pH? What happened to the pH when you add the 10 ml of 0.1 molar NaOH?
You can expect it to go up.
It's going to go up.
Go up.
Okay. So what we're going to do now is we're going to determine the pH. So what is the pH of the solution after you mix or after you add the 10 ml of 0.1 molar NaOH to 25 ml of 0.1 molar acetic acid. So the thing that you're going to get here is you need to get the moles of the acid and the moles of the base. So how do you get the moles of the acids and the moles of the base? From your Gen Chem 1. So for the moles of the acid, it will be 25 ml divided by 1,000 times 0.1 moles per liter. So that is equals to what?
2.5 times 10 to the negative 3.
So this is 2.5 . So that means that's the available H plus that you have in the system. So you do the same thing with the base. So where do you get the value for the base? The 10 ml. And what do you get? Did you get that?
Yes.
Did you get those values, everyone? So what are we going to do now? So we're going to let them react. Okay, so I'm going to open an additional page here. I want you to remember these values. So you're going to have a reaction. So how many moles do you have of this? 2.5 times 10 to the negative 3 moles. And this one is 1.00 times 10 to the negative 3 moles. So when they react, what do you produce? You produce your acetate ion. What's the concentration of your acetate ion initially? Anyone?
0.
0.
0. Now what will happen? What will be the changes that happen here? So if you have this amount, you have this amount, you're going to react with that whole amount. And since you're going to react those amount, you're going to produce also the same amount. Check if you follow. Do you follow? Where those numbers came from? Hello?
Not really. Sorry, not really.
So what happened there? Why did we say we react with the 1 times 10 to the negative 3 moles, because that's the amount of your NaOH. So the NaOH will push the reaction forward. So you're going to utilize all of your NaOH. So that means that's the amount of your acetic acid that will react with it. And when they react, they're going to produce the same amount. Remember the minus X and the plus X? Those are the minus X and the plus X. So at the end, what happened? You're going to get the difference between the two. So what do you have in the NaOH at the end?
0.
All of them are used up. And this one will have
1.5.
1.5 times 10 to the negative 3 moles. And this one would have
1.5 as well. Oh,
no. You only have 1.00
oh because
times 10 to the negative
0.
3.
Mm.
Because you add it with 0. What do you get? So everyone okay with the values that we have here? Everyone okay here? So if we're going to get now, based on the Ka equals to the H3O plus or the H plus times the CH3 COO minus over and then what do? We rearrange this one. So you will have what? CH3 COOH times Ka over CH3 COO minus. Or if we're going to put the value here, this will be 1.5 times 0. 1.50 times 10 to the negative 3 times 1.8 times 10 to the negative 5. That's the Ka over 1.0 times 10 to the negative 3. What do you get? Calculate, what do you get? What do you get?
2.7 times 10 to the minus 5.
2.7 times 10 to the negative 5. So you get the pH of that. So that will give you negative log of 2.7 times 10 to the negative 5. And that is equals to what? Anyone? What's the corresponding pH?
4.57.
So that is equals to. Now, is there any shortcut to this calculation? Can we use this one? Can we use the Henderson-Hasselbalch equation? Yes or no? The answer there is yes. And all you need to do is look at the value that you have there. So try to see if you're going to get the same number. Please try.
Yes, it's the same pH.
What do you get? Did you get the same number? Hello?
Yes, I got the same number.
I got the same number.
So what does it mean? If you have a weak acid reacting with strong base, okay, the pH before they reach the equivalence point, what you're going to do is just treat it as a buffer to get the pH, or you can do the long one if you want. So if we're going to go back, so from 2.87, after we add 10 ml, it now becomes 4.57. Now, does this number make sense?
Yes, yes, we expected the pH to be higher.
You expect the pH to be higher. Okay? So, let's try to solve the other one. So again, we just monitoring here the pH. So we know we have what? 2.5 times 10 to the negative 3 moles of the H plus. So that's one will remain the same. So the one that's changing is the hydroxide. So what do we do with this one? So we replace this with 25 ml over 1,000 ml per liter times 0.1 moles per liter. So this now become 2.5. So what can you say about the number of moles of the hydroxide and the H plus? They are now the same, right? So what will happen now to the reactions that we have? So we still do the same thing as what we did earlier. So what do we do now? We put both of the values there. So what will happen? You're going to react it with the same amount. And it's going to produce the same amount.
Professor, I have a question.
Yeah,
The only thing that's really confusing me is like, where did you get the -3 exponent from?
that's the one that's given. That's the number of moles that you have. That one. That. That's not clear to you?
So are we getting the number of moles from 0.100? So the 100 would be the -3?
You're getting it from converting your ml into liters and multiply it with 0.1.
Okay, got you. Got it.
Okay?
Mm-hmm.
Professor, I have a question.
Okay?
Could you go back to the main page?
So this is what happened. So what's the difference of this at equivalence point compared to the one before? No one among the reactants are present. All of them are reacted. Okay? But if you're going to look at the equivalence point, both the acid here and the base are 0. So where do we get now? We base it now to the concentration of the salt. So what will be the concentration of your salt here? So you have the number of moles divided by what? What is the volume of this?
50 mLs or
Okay,
0.005 liters.
so it equals to 50 ml divided by 1,000. Now you may ask yourself, where did you get the 50 ml? Where did we get the 50 ml?
25 mLs from the acid and 25 mLs from the base.
Very good. 25 ml from the acid, 25 ml from the base. So at the end, that's the total volume that you have. And if you have this one, this is equals to what? How many molar do you have there?
.05 molar.
So this is now equals to 0.05. Now what happened here? This is a salt, right? And what do you expect? The pH of a weak acid reacting with a strong base? What would be the pH? Will be equal 7 or more than 7 or less than 7?
Greater than 7.
So greater than 7. So what happened here? We have this salt. They will dissociate to give you this one. Now the question is, which ion hydrolyze?
The acetate ion will hydrolyze.
So the one that hydrolyze is the acidic one. Because that's the one that came from a weak acid. So you're going to have a reaction wherein you have this. Hydrolyzing with water to give you CH3COOH plus OH minus. And then you do the same thing. So this is what? 0.05. You don't have anything at the beginning. Then this is what? Minus X. This is plus X and this is plus X. So at the end, this is 0.05 minus X and this is X and X. So what do you have now in terms of K? What K do you have here? KA or a KB?
It's KB.
That's a KB. And then what you have here, you have an X times X over 0.05 minus X. So the KB, where do you get it? 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. Because you don't have the given KB, but you have the Ka of your acetic acid. And then you have your X squared and then 0.05 because you drop the X there. So the KB that you have here would be around 5.6 times 10 to the negative 10. So you multiply it with the 0.05 equals to X squared. So X is equals to what?
5.2 29 times 10 to the negative 6.
So that would be 5.29
29.
times 10 to the negative 6. Now, what is the x here?
Concentration of hydroxide ions.
So the x here is the concentration of your hydroxide. So you can get the POH, which is equals to what? Log 5.29 exponent negative 6. So that's around 5.27 or 28. So the pH will be equals to 8.72. Analyze. Question. Question?
How did you get 8.72?
14 minus 5.28. Question? So if we go here, this now becomes 8.72. Now the last one. So again, we have the 2.5 times 10 to the negative 3 moles of the H plus, but this now becomes 3.50 times 10 to the negative 3 moles of hydroxide. So where did I get this one? 35 divided by 1,000 times 0.1. So I do the same thing. So which one now is the one that is in excess?
Sodium hydroxide is in excess.
So just to do the same thing as earlier, so you don't have anything here, and then you're going to, it's not minus 2.5, it's just what we call 2.5. Why? Because the acid is only 2.5 times 10 to the negative 3 moles. And you're going to form also 2.5 here. But what happened here? Which one dictates the pH? So the one that dictates the pH here is your hydroxide. So all you need to do is find what is the OH concentration that you have there. So you have that moles divided by what volume?
0.06 liters.
So it is 35 plus 25. So that is divided by
1,000.
60 over 1,000. And this will give you how much concentration? Anyone?
0.0167 molar.
So that is equals to 0.0167, right? Now, what is this? The hydroxide. So you get the POH. That is equals to what?
The POH would be 1.78.
So this is 1.78. And what is the pH?
Twelve 12.22.
So the pH is 12.22. So let's analyze. Okay. So from 2.87, you add 10 ml, it becomes 4.57. You add 25 ml, it becomes 8.72. You add 35 ml, it becomes 12.22. Does it make sense? Does it follow this?
Yes.
So 2.87, 4.52, 8.72. And then when we add 35 ml, it's 12.22. So let's try this one. A strong acid and weak base. So if you have a strong acid and weak base, the pH at the equivalence point is less. And if we're going to look at this in this way, you're adding strong acid here to a weak base. So the pH becomes lower. And let's try to solve this one right away. Calculate the pH, the equivalence point when you have 25 ml or 0.1 molar ammonia titrated by 0.1 molar HCl. So what do you think is the pH when you are asked, okay, the pH of the equivalence point at this condition? So what do you think is the volume of your HCl? How do you get the volume here? So usually you have C1B1 equals to C2B2. So you have here a 25 ml times 0.1 equals to, you don't know the volume, and then you have 0.1. So as you could see, it has the same concentration. So most likely it's going to have the same volume. So if you're going to solve here, the same thing that we do, NH3 plus the HCl producing ammonium chloride. And since they have the same what? Volume and concentration, so this is just around what? 2.50 times 10 to the negative 3. And then all of them will react. To produce the same amount that react. So in the end, you don't have this, you don't have this, but you have this one. Now this is what? A salt. And this hydrolyzed to give you ammonium ion and chloride ion. And between the two, okay, Which one will hydrolyze?
The NH3 plus will hydrolyze.
The NH4 plus. It will hydrolyze to give you NH3 and H plus. So what's the concentration now of your ammonium chloride?
Concentration should be 0.05 molar.
So 2.5 times 10 to the negative 3 moles. So that's divided by 0.050 liters. So that will give you around
0.05 molar.
0.05. So that's the volume that you have. That's the concentration that you have here. Nothing, minus X plus X plus X. And you have here 0.05 minus X. And then you have X here and X. And then from this, what do we have? Ka or Kb?
Ka.
Ka. Now, usually the one that will be given to you is the Kb of NH3, which is 1.8 times 10 to the negative 5. So to get the Ka, 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, and you have here X 0.05 minus X. So this will become 5.6 times 10 to the negative 10. So this is X squared over 0.05. So your X is equals to what?
(5.27 times 10 to the negative 6).
5.27 times 10 to the negative 6. And this is your H plus. So to get the negative log, that is equals to this is what you get?
Yes.
Analyze. Question? So do you think you can get a problem like that in the exam? Okay, so I want you to go over this in a recorded what we call video. So the next thing that we're going to talk about is the acid-base indicators. So why do these indicators useful? Okay, why do you think they have the ability to change color at different pH? So it has something to do on the form that they have. So when you look at the indicator, if you look at the overall reaction of the indicator, so usually this is their form. The protonated indicator dissociating to give you an H plus and the protonated indicator. So what happened? This is what we call, has different color as this one. So that's the basis of your indicator. And if you're going to look at the difference that they have, so if the concentration of your protonated indicator over the deprotonated indicator is over 10, so most likely the color of the acidic indicator predominates. But if it's the other way around, where the deprotonated indicator is higher than the protonated indicator, it's the color of the conjugate base that predominates. So you have a thymol blue in the acidic range, okay? 1.2 or less, it's red. In the basic range, 2.8 or over the 2.8, that's going to be basic. So what do you think is the color at this range of these two? What it is that you learn when you add red with yellow, it will give you what color? Anyone?
Orange.
Orange.
So that means in the transition, okay, within this range of 1.2 or 2.8, the color of thymol blue is orange. But if it's lower than 1.2, it's going to be red. If it's higher than 2.8, it's going to be yellow. So it's the same thing as the one that you have here on the other, what we call indicator. Now, there's one unique indicator that they usually use. They call it the red cabbage extract. So if you're going to look at this red cabbage, okay, or the violet cabbage, if you're going to look at the color of the extract at the different pH, it's going to give you this color. This is due to the presence of the so-called anthocyanins, where at different pH, okay, there are different form of anthocyanins that dominate depending on the color that they have. Now, if you're going to look at the titration of a strong acid with a strong base, so these are the possible indicator that you can use. So commonly the one that is being used is phenolphthalein, and the one that phenolphthalein look is the changes in the pH at around 9. So if it's over 9, it's violet, or what we call light pink. If it's below 9, that would be colorless. If you do the methyl red, it's yellow above 7 or 5, and red, okay, if it's below 5. If it's a thymol blue, the same thing at above, let's say pH 2, that's yellow. Below 1.2, that's going to be red. So the question now, what indicator are you going to use here? And also here, and also here. So this is what? A strong acid, strong base titration, strong base, weak acid, or weak acid, strong base titration, and a weak base, strong acid titration. So try to, let's say, use the table here to determine what indicator you're going to use. I give you time to think before we go back. Okay, 2 minutes. Okay, so have you chose the thing now? What do we use here? pH 7. So we look at about here. So which one is the transition between pH 7? So I would say these two, right? The crescel red and the bromthymol blue. So in the exam, you can ask that question, but they will give you the pH range because you don't need to memorize them. Okay. So if you have around pH 7, so we might use this, what we call bromthymol blue and the crescel red. Or we could say, since the pH 7 is the basis there, we can get here all of them, okay, that change from 4 to 10. The exception that we're going to have here, we could say, is the thymol blue, the bromophenol blue, and the methyl orange, because they're usually what? Less than 7. But if you're going to look at the methyl red and all of the above here, you can use them. Okay. Now, for the one that is in the weak acid strong base interaction, we could say we're going to go with what? The crescel red and the bromthymol blue. This one, I think it's hard. So this is the one that is above pH 0.7. Because you're not sure here. It might be just what? Phenolphthalein. All of them will be violet or light pink for the phenolphthalein. Now for the last one here, which is the weak base with a strong acid, I think the suitable one that we have here is this thing here. Okay. Question so far? Question?
Yes, can you go over figure 16.6 again? Why you chose the pH?
Which one? This one?
Yes.
So you're going to look at the pH wherein they're going to change. So where do they change? They change at the pH that is less than 7. So in that case, you're going to go on this one, the one that is less than 7. So this methyl orange until the thymol blue, these 3.
Okay, thanks.
Question, the others? No pregunta? Before we go to the next one, which is solubility, equilibria. So what did you learn in your Gen Chem 1? In your Gen Chem 1, you have the solubility what? You still remember the so-called solubility rules? All nitrates are soluble. All chlorides are soluble except silver, mercury, and lead. You still remember that? Hello?
Not really.
So in the solubility rules that we have in Gen Chem 1, we have this what we call qualitative distinction between soluble and what's the other one? Insoluble. Now here in Gen Chem 2, the thing that we know is insoluble, they're not really insoluble. It just happened that the amount of solid that dissolved is small compared to the one that we call the soluble materials. So for instance, if the soluble materials has grams per liter, so there's several grams per liters that can dissolve in a liter of water. For the insoluble, what you have there is a unit of milligrams per liter. So when we say all chlorides are soluble except lead, silver, and mercury, okay? If we're going to look at this, the lead chloride, the silver chloride, and the mercury chloride, they are soluble, but the amount that they have is grams per liter compared to the other chlorides. So for instance, we use that as an example. Okay, silver chloride producing silver ion and chloride ion. So since the amount is so small, we could represent them as in equilibrium. If it's soluble, like let's say NaCl, how are you going to write it? You write it like this. So what's the difference between the two? Do you see the difference? Do you see the difference, class, between the two equations?
One is one direction, the other one goes both ways.
One is one direction, the other one goes both ways because NaCl is readily soluble. For the silver chloride, only a small amount of the silver chloride will dissolve. So that's the difference there. ¿Entiende?
Yes.
Do you get that? Okay, now, how are we going to represent this solubility here? So there is a corresponding equilibria or equilibrium for this, and we call them the KSP. And if you're going to look at this, we still apply the concept of equilibrium as we learned from chapter 14, wherein you're only going to write the aqueous solution or the gaseous state. So KSP now is equals to silver plus times chloride ion. And KSP is called the solubility product constant. Okay, so if you're going to look at the KSP, so this is the solubility product constant, and they were able to establish this value by getting the molar solubility. So if you are asked to write the KSP expression, you just follow what you have learned from your chapter 14. So if it's magnesium fluoride producing magnesium 2+ and fluoride ion, this is what you have. KSP is equals to magnesium plus fluoride squared. And then if you have silver carbonate, you have here 2 silver ion and a carbonate ion. So you have your KSP equals to silver plus squared, because you have 2 here, times the carbonate. Now, as you could see, you don't include this one is because what? Why you don't include this in the expression?
You don't include solids or liquids.
You don't include solid or liquid. And you can also have this. And when you express it in terms of KSP, this is what you get. Okay? Now, what does this mean? So KSP is the one that we have at equilibrium. But you can also express it like Q. What is this Q? Remember in our what we call equilibrium, we have the K and the Q, right?
Yes, is it the concentration of products?
Okay, so both of them we could say is just the ratio of the products over the reactants. The only difference K is during equilibrium, Q is at any point in time except equilibrium. Now we can also express here if we have the ions that constitute, let's say, a given compound, we can predict if that compound will be precipitate based on the concentration of the ions that is present in the solution. We're going to what we could represent it as Q, but in other book and myself prepared, I want to what we could express it as IP. What do you think the meaning of IP? Anyone wants to guess what IP means? Ion product. So what does it mean? If you have the concentration of the ions and you multiply them and you compare it with the KSP value, if the Q or the ion product is less than KSP, you have an unsaturated solution, there's no precipitate on it. If Q is equal to the KSP, you have a system at equilibrium. And if the ion product or Q is greater than the KSP, then you have a precipitate. You will have some example of that when you do the problem calculation. But what I want to discuss to you next is, what is KSP? What does the KSP tells us? Basically, the KSP will give us an idea on how soluble a given substance is. We can compare the KSP of different product and we can predict which one is soluble and which one is insoluble. But there's what we call the limitation in doing that. We can only do comparison if they are of the same order. What does it mean? So they have the same charge, like +1 and -1, or +2, -2, or +1, -2. You cannot compare the KSP of a compound that has this and this. So for instance, if we have the same +1 and -1, we can do it at like this one. The silver chloride and the silver iodide. So we can compare which is soluble. How do we compare the solubility when they have the same type of compound in terms of the KSP? So usually, the lower the KSP, the more soluble it is. The higher the KSP, the more insoluble it is. So my question now, if I'm going to compare this silver bromide, silver chloride, and silver iodide, which is the most soluble? And which is the most insoluble? How are you going to answer that?
Silver
The
chloride
most,
be more soluble.
So which is the most soluble?
Silver chloride.
And the most insoluble? What silver is the most insoluble among the three that I asked you to compare?
Silver iodide.
Okay, so silver iodide. So if you're going to look at this, silver chloride is the most soluble because that has the lowest KSP. And the most insoluble is iodide because that's the one that has the highest KSP. But you cannot compare this value, let's say, with this one. Why? Why can't silver carbonate included in the selection? Is silver carbonate the same type as silver bromide, silver chloride, and silver iodide? Are they of the same type? So one here would have what? A positive one, negative one, a positive one, negative one, a positive one, negative one. What's the problem with this one? A positive one and
-2.
a negative two. So they're not of the same type. And later on you will know. Okay? Because usually the problem that we have in this portion is just of two kinds. Either you're given the KSP and you get the solubility, or you're given the solubility and you calculate for the KSP. So these are the two types of problem that you have here in the KSP. And if you're going to look at this, so either you have a molar solubility and just solubility. So look at the difference between the two. So molar solubility specifically, it is in terms of moles. When it's just solubility, it is in terms of grams. So how do you go from molar solubility to solubility and vice versa? What do you need?
You need the molar mass.
You just need the molar mass. Okay? So if you're going to look at the two types of problem that you have here, either you're given the solubility and you're asked for the KSP, or you're given the KSP and you are asked for the solubility. So the technique that we have here, before we do a calculation and then have a break, if you're given the solubility of the compound and you're asked for the KSP, what you're going to do is you convert that to molar solubility. So what do you need here? You need the molar mass. And once you have the molar solubility of the compound, you're going to convert it into ions and the cations. And what do you need here? The stoichiometric ratio. So for instance, if you have silver chloride, so when it dissociates, it gives you 1 mole of silver ion and 1 mole of chloride ion. If it's silver carbonate, when it dissociates, it gives you 2 moles of silver ion and 1 moles of carbonate. So that's what it means here. And once you have the concentration of the cations and the anions, you can get the KSP. Now, if it's the KSP that is given, look what happened. This is just it's just this one going the other way. You're going to look at the concentration of the cations and the anions. And then from that, you're going to get to the molar solubility of the compounds and then the solubility of the compounds. So to give you an idea how this is being done, so we solve one problem here and then we call it a break. So the solubility of calcium sulfate is found to be 0.067 grams. So calculate the KSP for the calcium sulfate. So what type of problem is this? The first one or the second one?
First type of problem.
Okay, so you're given the solubility here and you are asked for the KSP. So that's the first type of problem. So what do we need to do here?
Need to calculate the molar mass of the calcium sulfate.
Maybe, yep, we can calculate, we're given one here, but since this is an equilibrium problem, we always put the equation. So this is a solid, and then they will produce calcium 2 plus, which is aqueous, and sulfate ion. And then we could put here the initial and the changes. So what do you have at the beginning here? None. And what's the changes that you have here? So we can use the value S instead of X. Okay? And then, what do we have at equilibrium? S and S. So if we're going to express this KSP is equals to what? Calcium 2 plus times SO4 2 minus, or S times S. And if we do that, what will happen? We need to get what S is. So we can start with 0.67 grams per 1 liter solution. And then we can convert this to the molar mass. So for every 1 mole, you have 136.2 grams. So how many moles of calcium sulfate do we have there per liter solution?
I got 4.9 times 10 to the negative 3.
So you have 4.9 times 10 to the negative 3. So can we say this is the S? Class, can we say that's the S? Anyone?
Yeah. Yes.
So we could say that's the S. So if we're going to substitute it here, 4.9 times 10 to the negative 3. Okay, so whatever the concentration of this, that's 1:1 mole ratio. So what is your KSP?
(2.4 times 10 to the negative 5).
How about the others? Times 10 to the negative what?
5.
How about the others? How about the others? Were you able to get that? Were you able to get that, class?
Yes, Professor.
So we stop here, and then we resume by 11 o'clock. There's no quiz yet. Okay, we might have the quiz by the end. But for now, okay, we're going to have a break. Okay? So let's have a 23 minutes break. We're back. Are you there?
We're here.
Yes, Professor.
Just uploading the thing. Okay. The next one, I think I'm missing some portion here. But if you're going to look at the question here, so I'm just going to write the question. Calculate the solubility of copper hydroxide in grams per liter. So the starting point that we have here is we're going to have the KSP. And if we're going to look at the KSP of copper hydroxide, so we're going to look at here, that's 2.2 times 10 to the negative 20. So the way that you're going to do this one is from the KSP, you're going to get the gram solubility of your copper hydroxide. So if we're going to look at the equation for this one, this is what we're going to have, right? So you have a plus S there and a plus 2S because you have 2 hydroxide for every copper hydroxide. So if we're going to look at the KSP, so we're going to put it as copper 2 plus times hydroxide squared. And then we're going to replace it with the expression here. So S2S2 equals to 4S3. And we know the KSP to be 2.2 times 10 to the negative 20. Okay. Now, should we get the S here? What that S equals to? What is the equivalent of that S?
The concentration of copper 2 ion.
Your S is your what? Molar solubility. So if we're going to calculate this one, the 4S cubed equals to 2.2 times 10 to the negative 20. How are we going to do that? You divide both sides by 4 and get the cube root. And S is equals to what? Please do the calculation.
Comes out to 1.77 times 10 to the negative 7.
1.77 times 10 to the negative
7.
7. So that's moles per liter. Right? Now, are we done with the problem? As I have told you, the one that's being asked is grams per liter. So what we have is just this. And whatever the problem that we have there, all we need to do is multiply this with what?
Molar mass.
The molar mass of your what we call copper hydroxide. So you have 97.57 grams per 1 mole. So that will give you how many grams?
(1.72 times 10 to the negative 5).
So 1.8 times 10 to the negative. Question. Question, class.
Professor,
Yes.
on my calculator, when I inputted the cube root of 2.2 times 10 to the negative 20 divided by 4, I'm getting an overflow message. Am I doing it wrong?
Maybe you're doing it wrong.
Okay.
How about the others? Were you able to get it? So you just observed, or you just did two types of calculations in solubility. One, given the molar solubility, and you got for the KSP. And the other one, given the KSP, and you're asked for solubility. So the next thing that we're going to have is look at the given expression here. So this is just the relationship of KSP with molar solubility, like what we did right now. We have a KSP equals to 4S cubed. Okay, so if you're going to look at the expression here, if it's 1:1, KSP is equals to S squared. The one that we solved right now is just that one. And to get for ds, you just divide both sides by 4 and get the cube root. Now, if you have the KSP equals to 27 with the 4th power, then you just divide both sides by 27 and get the, how do you call that? The 4th root. But we're not going to have problems like that. That's just be too much on your what we call part. Now let's go on another way wherein we're going to use the so-called Q or the ion product. Okay, so using Q is just predicting if you have concentrations of ion, if there will be precipitation of the given compound. So for instance, this one, Exactly 200 ml of 0.4 molar of barium chloride are mixed exactly with 600 ml of 0.08 molar K2SO4. Now the question, will a precipitate form? Now, what are the ions that are present here? Barium 2 plus, 2 chloride ion, 2 potassium ion, and sulfate ion. So what do you think is the product that will form to precipitate? Anyone?
Barium sulfate.
Because we need to know the product so that we can determine what's the given KSP. So if you're going to look at here, so the one that we're going to be produced is barium sulfate. So if we have this barium sulfate, we need to get the KSP of that, and that is equal to 1.1 times 10 to the negative 10. Why? Because we need to get the ion product and compare it to the KSP. So now that we know the KSP, what do we need to do? Anyone? What do you think we need to do? We need to get the concentration of this and this, because if you're going to look at the dissociation here, it's really like this. Then you have a KSP equals to Da2 plus times SO4 2 minus. So what we want to do is we want to get the ion product of that and compare it with the KSP. So we need to get what's the barium 2 plus concentration and what's the sulfate 2 minus concentration. So where do we get that? Here. So barium 2 plus, so 0.04, 0.0040. And then what's the initial volume? 200 ml divided by the final volume. What's the final volume?
800.
Everybody know where I get the 800? Class, you know where I get 800? I got 800 from 200 plus 600. Giving me what? If I have 0.04, I'm going to get 1.0 times 10 to the negative 3 molar. Everybody got this for the barium 2 plus concentration? Class, are you there?
Yes.
I'm showing up now. So the sulfate ion, on the other hand, you have initially what? 0.088, 0.08, 0.0080. And then you have 600 of that divided by 800. So you cancel out only the ml. So that would be
6.0 times 10 to the negative 3.
So what you're going to do, you have that as this concentration. And then you have this. So that will be equals to what? 6.0 times 10 to the negative
6.
6. So how do you compare the Q with respect to the KSP? Anyone?
The Q is larger than the KSP.
The Q is larger than the KSP. And that means we can answer the question here, will a precipitate form? The answer is what? Yes, precipitate form. And the reason for that is the ion product is greater than the KSP. Hello? You still follow?
Yes, Professor.
Now let's go on.
Hold on, if Q is greater than KSP, that means that precipitate will form?
Yeah.
Okay.
The relationship that we have for that is the previous slide. This one. There. So let's go on another solubility problem. So this one is selective precipitation. So you're taking advantage of your KSP value to precipitate a certain compound while the other compound or ion in the solution remains undissolved. So a solution contains a solution contains 0.02 molar chloride and 0.02 molar bromide ion. To separate the chloride ions from the bromide ions, you add solid silver nitrate slowly to the solution without changing the volume. So what's the concentration of silver ion needed to precipitate as much as silver bromide without precipitating silver chloride? So if you're going to look at the KSP of that, silver bromide, KSP, silver chloride, so you have it here in the table. So you have a 1.6 times 10 to the negative 10 and a 7.7 times 10 to the negative 13. So which precipitate first between the two? If you have bromide and chloride ions, you add silver ion. Which precipitate first? Anyone? So which precipitate first, the silver bromide or the silver chloride?
The silver bromide.
The silver bromide will precipitate first because that has the lower KSP between the two. So how much of the silver ions do we need to precipitate? Let's say we have this value. So KSP is equals to silver ion times bromide. So which one do we know here? We know the KSP is given there and we know the bromide. So all we need to do is divide both sides by bromide and then substitute it with the given value. So the answer here, that's the amount of your silver ion that is needed to precipitate. The minimum amount needed of silver bromide to precipitate, the minimum amount of silver to precipitate silver bromide. 7.7 negative 13 divided by 0.02. So I have here around 3.85. So what does this mean? You need that minimum amount for your silver bromide to precipitate. Now, you want to determine the same thing with how much silver do you need, silver ion do you need to precipitate out your chloride? So the same thing as you do here. Okay, the KSP of silver times chloride, and you divide both sides with the chloride. So you have here 1.6 times 10 to the negative 10 divided by 0.02. So what do you get there? I get 8. So how do we interpret this thing? So if we're going to interpret this thing, the silver ions that you need would be above 3.85 times 10 to the negative 11, but below 8.0 times 10 to the negative 9. So that's the range that you have. By doing this, you only precipitate your silver bromide. Your silver chloride will remain in solution form. But once you reach 8.0 times 10 to the negative 9, you're going to start precipitating your silver chloride. Question. Everything that we have now is solubility problems. Question, class, before we go with the common ion effect.
Yes, can you explain again the right lower
So the question that's being asked here, what concentration of silver ion is needed to precipitate as much as silver bromide as possible without precipitating silver chloride? So all we need to do is we determine what concentration of silver ion do you need to precipitate both. So we found out if it's a silver bromide, we need this amount. If it's silver chloride, we need this amount. We need this amount. So what we do, make sure we meet this amount to precipitate the silver bromide, but don't go over this amount or else the silver chloride will start to precipitate. So you need the silver ion concentration that is less than this 8.0 times 10 to the negative 9, but more than 3.85 times 10 to the negative 11. So you're precipitating only the bromide. But once you go over 8.0 or you reach 8.0 times 10 to the negative 9, you're going to start precipitating the chloride. Okay?
Thank you.
So the next thing that we have is the effect of the so-called common ion. So what is the so-called common ion effect? Okay, how does it affect the solubility? So we said before, when we have a common ion, what happened? It favors the backward reaction. So how does it affect the solubility? Okay, so the presence of the common ion decreases the solubility of the salt. Because what happened, let's say if you have a silver chloride here. So it produces silver ion and chloride ion. So if you have chloride from another source or silver from another source, it favors the backward reaction. So once it favors the backward reaction, what will happen is the solubility decreases. Okay? So let's try to look at the effect of this common ion. So we have a problem here about the calculate the solubility of silver chloride in grams per liter in a 6.5 times 10 to the negative 3 silver nitrate solution. But before we do that, what if we just going to get the silver chloride solubility first? So you could see the effect. Okay, so the KSP of this is 1.6 times 10 to the negative 10. So let's try to just solve this one. So what is this one? This is a S and a S, right? So if you get the KSP, that is equals to silver ion plus chloride ion. So this is just S times S. So KSP 1.6 times 10 to the negative 10 is just equals to S squared. So S is just equals to the square root of 1.6 times 10 to the negative 10. And that is equals to what? Anyone?
2.55 times 10 to the negative 5.
So this is what again, Tigran?
2.55
Is it
times
2.55? I get 1.25 or 1.26.
I got 1.26 times 10 to the negative 5.
That's what I get.
Yes, that's right. 1.26 times 10 to the negative
Okay.
5.
Now what happened if you have this one? So this is just in molarity. And if ever we're going to what we call make it into grams per liter, we're just going to multiply this with 143.4. So if we have square root of 1.6 exponent negative 10 times 143.4. So you have here around 1.8 times 10 to the negative 3 grams per liter. So what's the difference if you have a common ion? What happened in the common ion? So this 1s will have a 6.5 times 10 to the negative 3. And if you're going to look at the KSP of that, it will be S plus 6.5 times 10 to the negative 3 times S. And what can we say here? We could say that the S is so small, so that's just 6.5 times 10 to the negative 3S. So you have 1.6 times 10 to the negative 10 equals to 6.5 times 10 to the negative 3S. So we have here 1.6 exponent negative 10 divided by 6.5 exponent negative 3. So S is equals to what?
2.46 times 10 to the negative 8.
And if we're going to multiply that with 143.4, that's moles per grams per moles. So you get around what, 3.5. So what happened? So from here, when you have a common ion, it becomes this one. So from times 10 to the negative 3, it becomes times 10 to the negative 6. So it only shows that there is a reduction in solubility. Okay? So the presence of the common ion, which is in the form of a silver nitrate, reduces the solubility of your silver ion. Question?
Yes, I noticed in your second equilibrium equation, it's another silver chloride dissociating to the ions.
Yeah,
Okay.
but the difference here, you have a common ion already here.
The silver.
Because that's the one. Because I tried to show you what's the solubility of it if it's just in water, silver chloride in water.
Mhm.
So you have what we call a point of comparison. So as you could see here, there was a reduction in the solubility. Now, if the solubility is affected by, let's say, the common ion, what is the effect on the other hand of the pH? Well, it depends. How do you think pH affect the solubility?
Does it increase solubility?
Well, I told you it depends. Okay. Now, what we know so far, the presence of the common ion decreases the solubility. Now, insoluble bases, they said dissolve in acidic solutions, and insoluble acids dissolves in basic solutions. So for instance, the effect of the pH is conditional. So for instance, magnesium hydroxide, how do you make the solubility of magnesium hydroxide increase or decrease? So what is affected by pH here indirectly? What ions affected the pH here?
The hydroxides will interact with
Hydroxide.
the,
Okay. So how are you going to make it soluble? Or how do you make it more soluble and how do you make it more insoluble? Well, it depends on the amount of the hydroxide. If your hydroxide concentration decreases, it favors the forward reaction. Remember? If this one decreases, the forward reaction is favored. But if this one increases, the backward reaction is favored. Now the question, how do you decrease the hydroxide concentration? How do you decrease this? You
And acidic solution?
make it acidic. You lower the pH. But if you make it basic by higher pH, then the backward reaction is the one that is favored. Now the question now is, okay, I want to know at what pH this will be affected. So what do? I look at the KSP so that I can determine at what hydroxide concentration is the pH affected. And in solving that, I follow what needs to be done. And I found out that the pH or the hydroxide concentration that it is affected is at this concentration, which when converted to pH is around 1045. So what does it mean? When the pH is lower than 1045, what happened? What happened to your hydroxide? Will it be higher or lower?
Lower.
Okay, at pH less than 10.45, the OH is lower because the pH is lower. Okay, what happened to your hydroxide at that what we call pH lower than 10.45? It reacted with the H plus. So once you react your hydroxide with H plus, so that means there's no hydroxide here, so the forward reaction is favored and it increased the solubility of the magnesium hydroxide. However, if the pH is higher than 10.45, the hydroxide increases and the solubility of your magnesium hydroxide decreases. Does that make sense? Class?
Kind of.
Yes, at the lower pH, the hydroxides are getting used up, so
Yeah,
there's
the lower the pH, the lower is your hydroxide, because what happened, lower pH, you have H plus, and the H plus will react with the hydroxide. Therefore, your hydroxide concentration here decreases. So when it decreases, the magnesium hydroxide is more soluble because the forward reaction is favored. Now at higher pH, there are more hydroxide, so the backward reaction is favored. Hence, the solubility of magnesium hydroxide decreases. So let's try to look at it in terms of other compounds. So which of the following compounds will be more soluble in acidic solution than in water? So how are we going to solve this one? So you need to know what's happening in the reaction. So you break this down. So this produce what? Copper 2 plus and S2 minus. This produce silver ion and chloride ion. And this produce Pb2 plus and sulfate ion. And then what we're going to do, we look at the ions that we have here and see if they are, okay, conjugate base of acid. So S2 minus, where do you think it came from? What's the source of S2 minus? Can I say it came from this?
H2S.
HS minus. Because HS minus would produce me what? H plus and S2 minus. So what happened if you put a pH there? I mean, H plus. Do you think it will react with the S2 minus to produce HS minus? So remember, when you make it more acidic, that means there's a presence of H plus. Now the question, will that react with the S2 minus here, giving you HS minus? Will
Yes,
this
it will.
Yes, this happened. So when you have an acidic, what we call medium there, the S2 minus will react with the H plus to produce HS minus. Therefore, what happened to the solubility here? Increase, decrease?
Solubility increases.
How about the others, class? Will the solubility of copper sulfide increase or decrease at acidic solution? I'm trying to edit the poll, but I cannot what we call sign in. Okay, so based on this one, if you follow what I'm talking about, since your S2 minus reacted with the H plus there, so that means this will decrease, resulting in the forward reaction being favored and the solubility of copper sulfide increases. And if you're going to do this, it only happens when you have a weak acid. So as you could see there, the HS minus that you have there, that's a weak acid. Now, how about the chloride there? Where's the chloride coming from?
HCl.
So HCl, which is a strong acid. So since this is a strong acid, even if you have an H plus there, it will not react with the Cl minus. Because the one that is favored is the breakdown of HCl to H plus and Cl minus, not the formation of HCl. So in that case, you could say making it acidic will have no effect on the solubility of silver chloride. Now, how about the last one? If H plus is present, will it react with the SO4, 2 minus? Plus? Will there be a reaction?
You should get HSO4 minus.
Is this a strong acid or a weak acid?
It's weak.
It's a weak acid. The one that is strong is this one, but that's not that one. That was produced from this. So since this is a weak acid, this one will react with that one. So when that happens, this one decreases. So the forward reaction is favored. The solubility increase for the lead sulfate when the acidic condition is present. Question? Before we go with another system, this one, the basic one. Here you are asked to calculate the concentration of aqueous ammonia necessary to initiate the precipitation of iron hydroxide from a 0.0030 molar solution of Fe chloride. So how are we going to look at this? You need to determine the concentration of your ammonia. So if you're going to look at the reaction, so this is what? NH3 reacting with H2O to produce NH3 plus OH minus. And how is the Fe2 plus being affected there? So you have Fe2 plus reacting with hydroxide to produce FeOH2. Now, why did I say FeOH2? It says here. So if you're going to look at this, you get the KSP equals to Fe2 plus times can we say hydroxide squared? And that is equals, if you're going to look at the table, 1.6 times 10 to the negative 14. So what is given here? You're given the concentration of Fe2 plus. So if you're going to look at this will dissociate to give you the same amount of Fe2 plus. So if you're going to rearrange this one, so you have Fe2 plus times OH squared. So you have the 1.6 times 10 to the negative 14 divided by 0.0030. And what do you get in terms of the OH squared, OH minus squared? Five point
5.33 times 10 to the negative 12.
negative 12. And you need to get the square root of that. And that would be equals to what?
2.31 times 10 to the negative 6.
Now, this is the hydroxide that we need. But the one that's being asked is the amount of ammonia that you needed. So if you have this ammonia, you react it with water, it's going to produce NH4 plus OH minus. So you want to know how much you need. You don't have this, you don't have this. And then you want at least 2.3 times 10 to the negative 6. So that's the same amount that would form. That's the same amount that would form. So you have your x minus 2.3 times 10 to the negative 6. And you have both 2.3 times 10 to the negative 6 here in the product. So you have a KB. Okay, following that equation, NH4 plus times hydroxide over NH3. And then you replace it with the value that you have there. So you have 2.3 times 10 to the negative 6, 2.3 times 10 to the negative 6, and then you have here x minus 2.3 times 10 to the negative 6. And what is the KB here? So this is ammonia, so that's 1.8 times 10 to the negative 10. So what is the x equals to? The x should be at least 2.6 times 10 to the negative 6. That we'll not have a complicated problem like this one. So this should be 5, okay? Yeah, the KB should be given to you. Since ammonia and very common, it's 1.8 times 10 to the negative 5. Now, the last K that we have here in this part is this one. So the complex ion equilibria. Now, unlike the other K that we have discussed before, when we talk about the complex ion equilibrium and the solubility, so this happens when you form a complex ion. And if you're going to look at the complex ion, when you look about the solubility, it always have a charge. So that means it's always a soluble material. And if you're going to look at the K value that you have here, you call it the Kf. So if you're going to express the Kf for that, it's still the same products over the products of the reactants. It's still the same. The concept of the chemical equilibrium is still applicable here. Now, usually the Kf that we have, it's a big number, and the higher the Kf value, the more stable is your given complex. If you're going to look at the value of your Kf here, what can you say? Compare it to the Ka, Kb, Kw, Ksp. What can you say about the Kf value? Anyone?
Much larger.
Yeah.
Okay. So as you're going to look at this, they are 10 to the positive number, not 10 to the negative as what you say in the Ka, Kb, Kw, and Ksp. So that's the main difference of the K value that you have. So most likely this is what? One direction reaction. So if you have a complex ion, it's a one direction reaction. Okay. It's just that it's not really that the reactant will be zero. No, what happened is you just have a very small amount of the reactant left when the reaction takes place. So for instance, if ever we're going to have a calculation here, so you are asked a 0.20 mole quantity of copper sulfate added to 1 liter, to a liter of 1.2 molar ammonia solution, what is the concentration of the copper at equilibrium? So the way you solve this is you have to write what's the reaction that is happening. So you have copper reacting with ammonia, you're going to produce the copper ammonia complex. Okay. So if you're going to look at the Kf here, what's the Kf value? I mean Kf expression. So you will have copper ammonia complex equals to copper 2 plus times NH3 to the 4th. And if we're going to look at the Kf value of this one, that would be equals to 5.0 times 10 to the negative 13. No, not 13. No, 10 to the 13 as shown here. This one. And then, what do you think is the copper ammonia complex that will form? So what do you think is the amount of the product? So you have 0.20 moles of this one. Right? So what can you say about the relationship between copper 2 plus and the copper ammonia complex? The mole ratio, it is what?
1:1.
1:1, right? Now, you don't know now what is your X, what is your copper. Because remember, at the beginning, you have 0.20 and you're going to produce 0.20 of that. But you know, some of that amount will remain unreacted. So that's the X. Now, how much ammonia do you think will react with it? So 0.20 times what? 4? Give you what? So let's look at the reaction. So initially you have 0.20 of this and then 1.20 of this. You don't have that. And then how much you're going to react? So you're going to use up all 0.20 and then you're going to react what? 4 times 0.40. So that will be 0.80, right? And you're going to produce 0.20. So at the end, you might say this is 0, but that's the one that we're going to determine. And this one is 1.20 minus 0.80, that will give you 0.40. And this is 0.20. That's how you end up with that value. So this one is the x because it's not 0. It's a very small number. So here this ends up with 0.40 to the 4th. You follow that? Why 0.40? You have 1.2 and then you have 0.2 of your copper times 4 of that. So 0.80 of that react with that one. So you only have 0.40. So what's the x that you get here? Which is the copper 2 plus concentration. It's a very small number, but it's not 0. What do you get? Anyone? So 5 exponent. So 0.40.
Got 1.56 times 10 to the negative.
If we're going to look at this, this will become 0.0256, right? Times 5. Which is 0.20 divided by the 1.28. I get around 1.6 times 10 to the negative 13. That's what you get?
Yes.
So it doesn't really go to 0. It just goes to a small value. And then you calculate the molar solubility of silver chloride in 1 molar ammonium ion. So we're not going to solve this. I can promise you we're not going to have problem like this one in your exam. But the thing that I like you to know, what happened if we have that what we call silver chloride, okay? So in pure water, when you have that, this is the silver chloride. And then when you add ammonia, what happened is some of them is dissolved until such time all of them dissolve to form the silver ammonia complex. So the presence of this what we call ammonia there is just to remove the silver from the silver chloride. So what happened? Instead of silver chloride existing, some of the silver, or if not most of the silver, will complex with your silver with the ammonia to form the silver ammonia complex. Hence, you're dissolving the silver ion in the solution. So it's not existing as a precipitate. It exists as a soluble ion. So that's what happened of the complexation on the solubility. So if a complex ion is formed, the solution is soluble. And if you're going to apply what you have learned in terms of the solubility and the complexation, there is an experiment. I'm not sure if you do it in your 112, wherein you separate ion based on their precipitation reaction. So you have the group 1, taking in consideration the solubility of chlorides, where it is insoluble in silver, mercury, and lead. And then you have the group 2, so this is the one that sulfides in acidic solution. And then you have the group 3 cation, so that's the sulfide in basic solution. Okay? And then you have the carbonate soluble or insoluble stuff. So this is the group 2A, barium, calcium, and strontium 2 plus. And the one that are what we call the soluble ions. You have the K plus, the Na plus, and the ammonia. To test them, you do the flame test. This table will not be given in your what we call class. The thing that you need to remember here is what's the precipitating agent for group 1, 2, 3, and 4. And the way you do that thing is this one. So all cations, when you have at the HCl plus, the HCl or the Cl plus, minus, this is the one that precipitates. If you add the S2 minus, in acidic, this is the one that will come out. In basic, this is the one that come out. And then if you have the carbonate, this is the one that will come out. And the one that remains still not precipitating are the soluble ions. And the way that they do this is doing the so-called flame test, because each of them has their signature, what we call color of the flame. So until this is the coverage of your exam in 2 weeks. So your second exam will be on November 20. So that's the coverage of your second exam. And if you're going to look at our schedule, we only have, if I'm not mistaken, 4 more meetings. So if you're going to look at this, what are the dates that we're going to meet? 13, 20, and then in December, 4 and 11. So we're going to have a tight schedule remaining. And this is exam 3. And this is exam 4. Right? So we're going to go with the 17 on 13. And then we might finish it 17 after the exam and then starts with 18. And then we go everything on the 18 on 4. And then we have the exam on 11. So our numbers are already, we could say, almost done. And everyone, what we call, should be ready with the remaining days. So what will happen is I'm just going to post you, as I promised, like recorded problem solving. Okay. Now the thing is, I have to be direct with you. If you still didn't do well in your second exam, it's going to be a challenging time for you to pass the course. I just want to be honest with you. Because what did I say about the second exam? The second exam is what?
The easiest.
The second exam is the easiest exam. And I'm so happy most of you improved your score. But I'm also sad that some of you okay, still has the same score as the previous one.
Professor, you say you're gonna drop the first one, right?
Well, it's still subject to my what we call negotiation with the other instructor. But most likely, I think she will agree with me. So question.
Wait, Professor, I'm sorry. I checked the syllabus. I wasn't able to see the grading criteria like A plus A, B minus B, C, something like that. I didn't see that. So,
Because we adjust depending on the what oh no, we don't adjust. We follow the college grading. You don't look at it at the syllabus because you follow it directly from the York College. So if you are interested to that because you really want maybe to get an A, which I always tell my students not to be after the grade because you end up frustrated. So this is the grade numerical value. So this is based on the York College grading. We don't put it in the syllabus because it's understood that we follow the grading system of the college. But I always tell my students, don't go after the grade because you're just going to be disappointed and ending up cursing me. What do you need to do? What's my advice to you? Make sure what? You learn something.
yeah.
And the grade will come after, easy. So that's what we call the numerical value that we have. So that means the last month that you're going to have will be one hell of a month for you in chemistry. And I don't know what is going on in your Alex. If you want to do well, I think your Alex, you should perfect the Alex. Because sometimes Alex is the reason why you don't do well. Even if you're doing well in your long exams, but when the Alex comes in, and that is a sure 250 points, and you get less than 100 points then your grade will really be affected. That's why I told you, even if I give you additional stuff to do to at least give you a passing grade, at least in the lecture part, which is 50%, you mess up the Alex, you mess up the final exam, you're going to still fail the course.
Professor, is the lab and the lecture, are they the same or do they have like separate grading?
What?
Do you grade the lab and the lecture, are they like the same
No,
point?
lab is different. Lab
Oh.
is 112. You have your own grade there. I don't care what's happening there.
Oh, okay.
What is the number of lab? Is it the same as 111?
I was just confused, sorry.
The reason why they separate the lab and the lecture, because before many passed the course because of the high lab grade. So right now what they do is, you fail the lecture, you fail the lab. I don't know if that's applied. But that's the reason why they separate the lecture and the lab, because they're not doing well in the lecture, but they have a high lab score, they end up passing the course. But as I could told you, lecture is 111, lab is 112. I don't care about the lab, and the lab has no say in 111. So I'm happy, as I've told you, that most of you, your score increases in the second exam, but I'm still sad because some of you still has the same score as during your first exam. So I don't know what to do. I already gave you the stuff that could improve you, and we're going to maintain that thing. So the coverage is already what we call over for the for the third exam, and I'm giving you 2 weeks to prepare for that. We're going to have a quiz today. I was not able to open it earlier because the signal is really problematic here, but I think it improves now. So what we're going to do next meeting, we're going to start with 17. We have no choice. If we can finish it, we'll finish it. And then I want you, starting this weekend, to go over the problem set. Okay? Try to prepare for the what we call third exam. And if you're listening in the lecture, I show you the possible problems that will come up in the third exam. But I have a warning to you. If the second exam is the easiest exam, based on my class experience, the third exam is the worst one. But I have different preparation that I have this semester compared to the previous one. So I already gave you some stuff wherein you make sure that you go over them, the recorded lecture that we have to prepare you for the exam. Okay? So what are the possible questions that will come up? I told you 20 points. You get the pH of a strong acid, strong base, weak acid, weak base, and the salt. That's a 20 points problem. And then another problem that you have is a buffer solution. That can be a 10 to 15 points problem. Another one is titration. So if you're going to look at our lecture, initially the titration is really long. Okay, it can be a 10 to 15 or 20 points problem. And then we have the solubility problem. So those are the problems that will come up in the exam. I didn't tell that during the time that I'm doing this, but I'm telling it to you now so you can prepare yourself. So that's the difference that we have this semester and the previous semesters, where the third exam is the worst one. And I'm going to give you also the same thing that I give you in the second exam, the chapter problems. So I'm hoping maybe at the end of the weekend, next week, that it will be available. And I don't know if you're going to agree with me, but the problem set or the reviewers really helps, right?
Yeah, it did, Professor.
So maybe just use that, so that my effort of posting the solutions for those questions will not be meaningless. Because remember, if you repeat the course, it's you who's going to do it again. If we see each other again, you're going to be bored with me because I'm going to talk the same stuff. I'm going to give the same joke. And a joke that was heard before is not funny the second time around. So it's your call. Okay? So question. Because I'm going to leave you now, but make sure you take the quiz. So I have a 20-minute quiz. It's a 4 points question, but make sure you prepare your calculator because there's a calculation that you have there. And then during the week, I'm going to give you also other what we call quizzes. Is that okay with you? Maybe 2 quizzes during the week.
Yes, it is for me,
Is that
Professor.
okay with everyone?
Yes, Professor.
Okay. And then
Yeah, I'm saying no.
Exam 3, we're going to what we call, give you again this what we call exam dry run, just to prepare everyone. But as I've told you, we have only what, 4 more meetings, and in 2 meetings of that, you have exam. Okay? So question? So the exam is until 1 o'clock.
Professor, is the exam,
So quiz,
is the quiz today due based
1
on what
o'clock.
we, okay, wait,
It's about buffer.
on buffer?
Yep.
Oh my God.
Do you have any question?